What if I told you that electrons are not just tiny particles orbiting around the nucleus, but also mysterious waves that exist everywhere at once? This mind-blowing idea changed science forever. Hi everyone, welcome to Chemistry Portal. I am Sudhanshu Kumar, and today we will explore the fascinating world of quantum mechanics and atomic orbitals. So first topic we will do here, and our main topic today, that is quantum mechanics. Mechanics. And first of all, in this course, in this session, we will not go in so depth of quantum because this course is our introduction to organic chemistry. So that's why we will not go so much depth, psi and all, okay. We will do a brief overview of the quantum mechanics, orbital, subshell, shell, electron, and all the things, okay. Yeah. So, for a very long time, electrons were thought to be tiny particles orbiting around the nucleus, much like planets around the sun, like this. Here, this is the orbit, okay, and this is your nucleus. Suppose here in the center of the atom we have nucleus here, and okay, this is your nucleus, right, and here you have electron, okay. So in the very old time, like for a long time, electrons were thought to be a tiny particles, okay, and that is revolving around the nucleus in a fixed orbit, much like planets around the sun. However, but in 1924, a French physicist named Louis de Broglie changed this perception. He proposed that electrons also exhibit wave-like property. Okay, listen me again. In 1924, see here, in 1924, Louis de Broglie, French physicist, okay, French physicist Louis de Broglie, he proposed that electrons also exhibit wave-like property. Okay? Now, electrons now the question is what? Now the question is electrons is particle or wave? Particle or wave? Okay, I will take a picture from here, okay, that is a good to describe this. Electron is particle or wave? See here. So actually, electron can behave as a wave also and behave as a particle nature also. Okay, various experiments has been done to prove this all. Okay, like electron has a dual nature, wave nature also, and particle nature also. Okay, so in the 1924, a French physicist proposed that electrons has wave-like nature. Okay, wave-like properties. Okay, so write it here. Electrons are wave-like property. Electrons has wave-like property or wave nature. Properties. Okay. Now, actually, this de Broglie idea was supported by combining the Einstein equation and that relates the mass and energy with Planck equation, okay, and that relates the frequency and energy. And this realization led to the development of quantum mechanics and which describes the behavior of electrons in atoms. So first of all, what happened? De Broglie combined the equation given by the Einstein and Planck equation. Okay, so see here, we know that energy equal to mc square, right? According to the Einstein equation, and this is equal to Planck equation hc by lambda. Okay, and this is valid for light or photon. Okay, and from here, uh, if you do the maths, you will get here lambda equal to h by mc, and that is for photons, right? And here we know that lambda equal to this mc equal to, that is nothing but it is a momentum, right? P equal to mv, right? So we can write here h by p. This is for photon, and by analogy we can say that de Broglie proposed lambda equal to h by mv. Okay, this is very very important. De Broglie wavelength, very famous, and this is valid for moving matter particle, electron, proton, neutrons. And here we are, because talking about electrons here, okay, so we'll take here mass of electron and here velocity of electron, and all the things we will take here about electron, okay. But this de Broglie wavelength, lambda equal to h by mv, this is valid for moving matter particles, and that particles can be proton, electron, neutron, okay. So this lambda is called de Broglie wavelength, okay, de Broglie wavelength, right? But how it looks like, how the electron can behave as a wave, okay, I will give you a feel by a picture. I will just copy paste here, okay. Oh, sorry. Okay. So here, see this picture. Here, this is your first orbit, but this electron is not moving in the orbit, okay. Electrons are moving like a wave nature, okay, understood, like this, okay. Like we have electron here, it will go like a wave, understood, around the nucleus like a wave, okay. And this is what de Broglie said, okay. De Broglie proposed that electrons also exhibit wave-like property, okay, understood, like this, we have a wave-like property, okay. And more detail we will talk about in the quantum mechanics when we do the physical chemistry, okay. Now it's our organic chemistry, introduction to organic chemistry, okay. So, but one more thing I want to tell you, how we can feel this wave, like how electron can behave as a wave, suppose you have a guitar, okay. Let me copy a picture of guitar here, okay. Guitar, this is your guitar, okay, fine. you have guitar here, right? So when you pluck it, it vibrates, right? In the specific patterns, right? And these patterns depends on how the string is fixed at both the end, right or not? And how you pluck it, okay? And that vibration, this vibration creates waves, and which that's the sound you hear in your ear, right? Understood? Okay, similarly, electrons around the nucleus does not move like planet. Okay, this is wrong. This is wrong. Okay, in the actually, electron do not revolve like a planet. Okay, around the sun. Understood? This is not the real picture. Instead of this, it behave more like wave. Understood? More like wave nature. And the electron positions is not fixed, but it form wave-like pattern around the nucleus, like this. Okay? Electron can be here also, electron can be here also, here also, here also, anywhere. Understood? Electron positions is not fixed. Already I told in the starting video. Okay? Clear? So when you pluck a string of guitar, and that vibration creates the wave, and which determine the sound you hear, right? Similarly, electrons also around the nucleus behave as wave. Understood? Just like the vibration, just like the vibrating a string, right? And the electron positions is not fixed. Okay, electron can be anywhere in this region. Understood? It is not fixed, right? And in the physics we have some equation to describe the string vibration, right? That is called wave equation. Similarly, here also, how electron behave around the nucleus, and these equations tells us where the electron is mostly likely to be found, similar to predicting the shape of a vibrating string. Okay, like we studied in the physics, right? We have equation for any waves, any sound waves, right? Similarly, the same equation that describe the string vibrates, wave equation also describe how electrons move around the nucleus and behave around the nucleus, and these equations will tell us where the electron is likely to be found. Okay, understood? Okay, and then the Schrödinger came, and then the Schrödinger came. Okay, Erwin Schrödinger. Now write it. Erwin Schrödinger in 1926, and in 1926, Erwin Schrödinger formulated the most widely used version of quantum mechanics, and his equations describe the motion of electron around the nucleus using a wave function. Okay, using a wave function that is a psi. We will not go into detail. Okay, already I told you this course is of introduction to organic chemistry, right? So in 1926, Erwin Schrödinger formulated the most widely used version of quantum mechanics, and that equation describes the electron motions around the nucleus using a wave function that is called psi. Okay, and according to Schrödinger, electrons are found in regions around the nucleus called atomic orbitals. rather than fixed orbit. Okay, Schrödinger told that electrons do not revolve around the nucleus in a fixed orbit. This is wrong. Okay, this concept is wrong. According to Schrödinger, he told that electrons do not revolve around the nucleus in a fixed orbit. Rather than electron found in the region around the nucleus that is called atomic orbitals, rather than fixed orbit. Okay. Now we will talk about in so much details what is called atomic orbital, what is cells, subshell, and all the things. Okay? Okay, fine. So let me take some diagram of onion. Okay? That will give you feel of subshell, cell, and all the things. Okay? So let's take an onion. Right? Okay, let me take an onion here. This is your onion picture. I will copy this. Right. See. Now, imagine an onion with a multiple layer, right? In the onion, we know that we have a multiple layer of layers of onion around the whole onion, right? We have like layers, understood? When you cut the onion, you will get layers of onion, right? Right. So each layer represents an energy level or cell where the electrons can exist. Okay. Don't think onion is the real atom. Okay. I'm just taking an example to simplify this concept that is called cell. Okay. What is called cell? Understood? So imagine an onion with a multiple layer, right? And each layer, this layer, this layer represents an energy level, okay, or cell where electron can exist, right? So I can show here. This is your first layer, suppose, first cell. I am saying this first cell, okay, first layer of onion, this one. This is your suppose first cell, okay, and here we have nucleus, right? In the center of the onion, suppose this is the atom, right? So in the center of the onion you have here nucleus, similar like atom, okay, right? And inside the atom you have here nucleus, and around the nucleus you have here cell, concentric cell, okay. This is your first cell, right? And the first cell, this is your close to the nucleus, very close to nucleus, okay. This is close to the nucleus, right? This cell is close to nucleus, right? Now the third cell, this one, this is called second cell, right? And now we have third cell. Similarly we have third cell, then we have fourth cell, and so on, okay, right? And each cell represents the energy level, right? Energy level, okay. So you can write here energy level cells equal to, cells is nothing but it is an energy level where the electron can exist, okay. Energy levels, right? Okay, fine. Now what the Schrödinger said? Schrödinger said electrons are found in the region around the nucleus called atomic orbital. Write this one, very important. Write this note. Schrödinger, according to Schrödinger, electrons are found in regions around the nucleus, right? And called atomic orbitals. atomic orbitals, right, rather than fixed orbit. Okay, okay, fine, that's fine. Okay, and atomic orbitals, these atomic orbitals are grouped, and atomic orbital are grouped into different cells, into different cells at different distance. Okay, at different distance from the nucleus. Okay, fine. Now see, first of all, we assume this is the atom, right or not? Okay, and we have here nucleus, center of the atom, and around the nucleus we have concentric cells. Okay, right, first cell, second cell, third cell, fourth cell, right, and this cell is nothing but these are energy levels. Okay, right, but Schrödinger said electrons are found in the region around the nucleus, called atomic orbital. It means, according to Schrödinger, electrons are found in the atomic orbitals, and these atomic orbitals are grouped, are lie in the cells. It means, in each cell you have atomic orbital, right? Every cell has atomic orbital. Inside the cell you have atomic orbital, and in that atomic orbital you have electron. Electrons are present there in the atomic orbital, right or not? Now let's see here. I will give you a very good flow chart to understand how it look like. Okay, see, first of all, atom, right? Atom, clear? Inside the atom you have cells, right or not? Concentric cells, right? Concentric cells. And we denote the cells by a small n. A small n is the cell number, right? Okay, we'll talk later in more detail. Okay, now concentric cell, right? Inside the cells we have a subcell. Okay, inside the subcell we have atomic orbital, and inside the atomic orbitals you have electrons. Electrons are present. Okay, see how this beautiful flow chart. Now there should be no doubt, okay, about this. See here, first of all, atom. This is your atom, suppose. Okay, sorry. This is your atom, right? Inside the atom you have nucleus here, right or not? And around the nucleus you have what? Cells. Okay, see here, cells, right? See, okay, and inside this particular cell you have again subcell. Inside the subcell you have again what? Atomic orbital. Inside the atomic orbital the electrons are located, electrons are present, electrons likely to be found in that particular atomic orbitals. Okay, right? Clear, everyone? Okay, so first of all, write the term. Some terms you have to write it. Okay, that is the important one. Okay, so write first of all cell. What is called cell? Cell is nothing but, a cell is the main energy level. A cell is the main energy level in an atom where electrons reside. Okay, and it is denoted by uh, a small n, okay, a small n, and these cells are like so we can say that here this first cell equal to n equal to 1, this is called n equal to 2, and this is called n equal to 3, this is called n equal to 4, right or not? This is the first cell, second cell, third cell, fourth cell. Or we can say that first energy level, second energy level, third energy level, fourth energy level. Okay? Or we can also denote or label as KLM, like KLM, NOP, and like that. Okay? Understood? Like this is your K cell, this is your K, this is your L, this is your M, this is your N. Like this we can also label these cells. Okay? Right? Right. Now see the subshell. What is called subshell? What is subshell? Subshell is a division of a cell. Okay? A subshell is division of cell. Right? This is a division of cell. Division of cell. Okay? Where electrons are further grouped based on their angular momentum. Okay, we'll talk about later this term angular momentum. Okay, angular momentum, right? Okay, we'll talk this later. What is called angular momentum? Okay, we will not go in so depth in this session. Okay, understood? We will discuss in this separate video in more detail. Okay, right? We have so many quantum number also. Principal quantum number, azimuthal quantum number, magnetic quantum number, a spin quantum number. That things we will not discuss here. Okay, I am giving you brief overview of quantum, electron, cell, subshell, and all the things. Okay, right? So subshell, how many types of subshell, right or not? So subshells is like subshells is labeled as S, P, D, F, right? These are subshells, okay? And each subshell, like suppose this subshell, right? It here, these are the subshell, right? These are the subshells, okay? These are subshell. SPDF, okay? These are just name given, okay? SPDF, subshell. Now, each subshell has a specific number of orbitals, of atomic orbitals, and can hold a fixed number of electrons. Okay? Each subshell means S. Inside the S, you are having a atomic orbital. Inside the P subshell, you are having a atomic orbital. Inside the D subshell, you are having a atomic orbital. Inside the F subshell, you are having a atomic orbital. Okay, clear? Right. Okay. Now I will draw some cells. Okay. Think in 3D. Okay. This onion layer. Think in 3D. you will get more feel. Okay, understood? Like how are the concentric cells are present around the nucleus. Okay, right. So now I will draw. Now I will draw here concentric cells. Okay. So take it here like this. Okay. Sorry. Right. Take one more. Okay. Take one more. Concentric cells. And this is a 2D, right? This is a 2D. Okay. I will try to give you feel of the by some image. I will try. Okay. So this is your I think this is good. Good to go. Okay. So here you have nucleus here. Inside the atom you have nucleus here, right? And inside the nucleus you have atom here. Okay. Before going to this part, I want to write a note. What is called atomic orbital? Atomic orbital. This is a very very important term. Okay, we should not leave this. Atomic orbital. Atomic orbital is a 3D region around the nucleus where an electron is most likely to be found. Okay, understood? I will tell. Okay, don't worry. And an atomic orbital is the 3D, three-dimensional region around the nucleus, where an electron is most likely to be found. Okay? Atomic orbital is nothing but it is a 3D region around the nucleus where an electron is most likely to be found. Okay? Clear? Yes. Now, so you have here first, here you have nucleus, and here this is the first cell, so you can write here n equal to 1, this is your n equal to 1, this is your n equal to 2, and this one n equal to 3, and this one n equal to 4, right? First cell, second cell, third cell, fourth cell. Okay? And now see, now it's a very very important. Okay, so in the first cell you have only S subcell. In the second cell you have S and P subcell. In the third cell you have S and P and D and F subcell. In the fourth cell you have you have here SPD only. Okay, in the third cell you have only SPD subcell, and in the fourth cell you have S, P, D, F, and so on. Okay, S, P, D, F, G and all. Okay, so see here, nucleus here, right? First cell, inside the cell you are having a S subcell, right? Now come to the second one, second cell. Inside the second cell you have two subcells. One is S, one is P, right? In the third cell, see here, you have three subcells, S, P, D. Inside the fourth cell, you have four subcells, S, P, D, F. So we can say that number of cell equal to number of subcell. Okay, we can say that number of cells equal to number of subcell present in that cell. Right or not? If I ask you, tell me how many number of subcells present in the n equal to 3. So what's the answer? 3. We have S subcell, P subcell and D subcell. Right or not? Okay. Now and how you can feel this, right? How you can feel this, how it will be existed in this cell. I want to give you a 3D image, okay, of nucleus, and around nucleus you are having concentric cells, and in that cell you have a subcell. Okay, let me just copy this picture, this one. See here. Suppose this is your 3D image of whole atom, right? Atom here, and here you have nucleus, right? Here. In the middle of this atom, you have here nucleus, okay? And this is your first cell, concentric cell. Think in the 3D, okay? Think in the 3D, feel the 3D, understood? Then you will realize how it look like, how the concentric cells are organized around the nucleus, okay? So this is your first cell. I will mark also here. This is your first cell, okay? And this red one, okay? This red sphere, this is your first cell. And now the green one, this is your second cell. Means n equal to 1 here, and here n equal to 2. And this one, blue, this blue region, whole blue region, okay, whole blue region. This is your third cell, and here the n equal to 3, and this is your purple region. See the purple, whole purple, understood? Right? Think in the 3D, okay? Don't think in the 2D, understood? Try to visualize it. So this purple region is your fourth cell, and in this fourth cell we can say that n equal to 4, right? Now see how the subcells are present here. Inside this area, inside this red region, whole region, you will have S subcell. See, you will have S subcell. Now in this green region, you have 2 subcell. See here, in the second cell you have 2 subcell, and these 2 subcell S and P will be present here in this green area. Understood? Green region, right? And now in the third cell you have what? S, P, D. All these 3 subcell will be present in the third subcell, in this blue region, whole blue region, okay? Think in the 2D, okay? Try to visualize in the 3D, okay? Understood? Now go to the fourth cell. You have 4 subcell, S, P, D, F. So in this case, think in this region, in the whole purple region, okay? Think in the 3D, and in this fourth cell, you have 4 subcell, that is S, P, D, F will be located in this region, right? And you can also observe here, when you go far from nucleus, right, the cell shape is going to be increased, okay? So how much far you will go from nucleus, the cell will increase, the cell size will increase, okay? See, a small, bigger, more far from nucleus. right or not? So this is like a 3D image of concentric cells, and in this concentric cell you have subshell, and inside this subshell you have atomic orbitals, right? Okay, and this is the flowchart I given to you. First of all, atom. Inside the atom you have concentric cells, and inside the concentric cells you have subshell. Inside the subshell you have atomic orbital, and in the atomic orbital the electrons are present. Electrons are most likely to be found in the atomic orbital, right? Okay, okay. Now, and note one more thing here. And atomic orbitals, write one term here, write one note. Atomic orbital has a characteristic shape. Okay, every atomic orbital has different shape. Okay, understood. Okay, atomic orbitals has a characteristic shape and energy, and occupy a characteristic volume of a space. Okay, every atomic orbitals has characteristic shapes and energy, and occupy a characteristic volume of a space in the atom. Okay, right. Now, now, now I will tell you something. Atomic orbital. Okay. Now see, in this subshell, how many types you have atomic orbital? Now we will discuss it. Okay. So in the S subshell, there is only one orbital. Okay, only one orbital. That is called S only. Okay, S atomic orbital. Right. Now in the P subshell, in the P subshell, you are having a three types of atomic orbital present in the P subshell. Very interesting. Okay, quantum mechanics is very interesting. Okay, okay. Inside the P subshell, okay, this P subshell, you have three atomic orbital, and that three atomic orbital, it is called px, py, pz. Okay, and all these orbital are degenerate atomic orbital. Degenerate atomic orbital, because all these atomic orbital px, py, pz, all are having a same energy. Okay, all are having a same energy. Degenerate means what? Same energy. Same energy. See here, first of all, S subshell. In the S subshell, you have only one atomic. Okay, sorry, this is the atomic. Okay, you have one atomic orbital, that is called S atomic orbital. Right. Now, in the P subshell, you have three types of atomic orbital. One is px, py, pz. Okay, and now these all atomic orbital in the P subshell are degenerate atomic orbital, means they are having a same energy. Okay, now in the D subshell, you have five atomic orbital. Five atomic orbitals, right? So first of all, you have dxy. These are the name of atomic orbital, okay? dxy, dyz, dxz, dx square ys square, dx square y square. Then you have dz square. Okay, these atomic orbitals are present inside this d subshell, and d subshell present in the cell. Okay, simple, right? See this flowchart. First of all, atom. Inside the atom you have cell. Inside the cell you have subshell. Inside the subshell you have atomic orbital. Right or not? Okay. So this is about atomic orbital, and here also. All these five atomic orbitals of d subshell also degenerate atomic orbital. Means they are same energy. Degenerate atomic orbital. And degenerate means why? What? Same energy. Same energy atomic orbital is called degenerate atomic orbital. Okay. Similarly, we can tell for F also. Okay. For F subshell, but it is a very more complex. Okay. And F subshell having a 7 atomic orbital. 7 atomic orbital. Okay. Right. We will not talk about here about the names of that orbital, okay, because that is so much complex and all, and that is not required now, okay, understood. So these are the subshell, and inside the subshell you have atomic orbital. Okay, clear? Right. Now you can observe here in the S subshell you have only one, right or not? In the S subshell you have only one atomic orbital. In the p subshell you have 3 atomic orbital. In the d subshell they have 5 atomic orbital, and in the f subshell they have 7 atomic orbital. It means if you add plus 2 you will get p subshell, right or not? If you have in the s you have 1, then how much in the p subshell? So 2 plus 1, 3 orbital. 3 atomic orbital. If you want to find the d, then go from p to d. So p having how much? 3, right? So add plus 2 more, you will get 5, right? And we have 5 atomic orbital. Then go from d to f. D having how much now? 5, right? So 5 plus again plus 2, you will get 7 atomic orbital. If you want to find for g, right? Again do it 7 plus 2, you will get 9 atomic orbital, like that. Okay, this is the general. Okay, understood? Okay, now write one note here. Note: maximum of 2 electron coexist in an atomic orbital. Okay, understood? Suppose if I ask you, we have here S subshell, we have P subshell, we have here D subshell, we have here F subshell, suppose. Okay, and now, and if I ask you number of maximum electron. So in the S subshell, see, first of all, in the one atomic orbital, we can fill maximum 2 electron. Simple. This is very, very important. Okay, this is very, very important. In an one atomic orbital, we can fill, or 2 electrons maximum can exist. Simple. Okay. So we know that in the S subshell you have only one atomic orbital. So 1 into 2, how much? 2 electrons we can fill in the S subshell, right? And then you have p subshell. So in the p subshell we have three atomic orbital, that is a px, py, pz. So it means we have 3 atomic orbital, and just now I said here we can fill maximum 2 electron in one atomic orbital. So 3 into 2, how much? 6. So here 3 into 2 equal to 6 electron we can fill in the p subshell. Now you have d here. In the d you have 5 atomic orbital, and now we know that one atomic orbital we can maximum fill 2 electron, 2 here, 2 here, 2 here, 2 here. So all if you add it, how much? 10. So 5 into 2, 10. So in the d subshell we can fill maximum 10 electron. Now comes to the f subshell. Similarly we have here 7. So 7 atomic orbital, but one orbital can take only 2 electron maximum. So 7 into 2 equal to 14 electron maximum. It can coexist. Maximum 14 electron we can fill in the S subshell. In the D subshell, maximum 10. In the P subshell, maximum 6 electron. In the S subshell, maximum 2 electron. Right? And now you can also find maximum number of electrons in a cell. Maximum number of electrons in cell. There is a formula also you can apply, 2n square, and this n is what? This n is the number of cell number. Cell number. If I ask you, tell me the maximum number of electron, tell the maximum number of electron in second cell. So what we will do? Simple. Draw here. One method I will tell you the general method, okay? Classic method, like how to do this. First of all, nucleus here, right? And then draw the orbit, first cell, second cell. Now we know that in the first cell we only have S subshell, right or not? This is where n equal to 1. And in the second cell we have 2 subshell S and P, right? Now we know that S is having only one atomic orbital. S having only one atomic orbital, 1, and but P having 3 atomic orbital. Right or not? See here, P we have 3 types of atomic orbital, px, py, pz. So now tell me, in the second cell, how many electron we can fill maximum? Tell me. In the S, we only have one atomic orbital. Now we know that in one atomic orbital, we can fill maximum 2 electron. Right or not? This is very, very important. So in the S subshell, you can fill maximum 2 electron. Right? And in the P subshell, because you have 3 atomic orbital and one atomic orbital can take maximum 2 electron, that's why 3 into 2, 6 electron. So 6 plus 2, 8, right? So in the second cell, maximum 8 electrons present. Okay, clear? And you can apply the formula also. If you go by the formula is 2n square, right? So we have here second cell, so 2 into 2 square, you will get here 8 electron maximum. Right? See? The answer will come same. This is your basic method, understood? And this is, you can say, like a trick or whatever. Okay? So, and if I tell you, I can make a chart here, one chart I can make here, okay? One chart I want to make here. So write here subshell, okay, and write here first cell, and here second cell, here third cell, and here fourth cell. Right, okay. So in the subshell, wait. Write subshell here, okay. Okay. Right. Okay, see, in the first subshell, in the first cell, how many you have subshell? See here, 1, right? So write it here, 1. And that is your S subshell, right? So write here S. And in the second cell, S and P, right? S and P, right or not? S and P. And in the third cell, you have S, P and D, right? And in the fourth cell, you have S, P, D, F. Now make one thing here. Now write here number of atomic orbital. Number of atomic orbital. Now you tell me. So here we know that in the S we have only one atomic orbital, and that is the S only. So write it here, one atomic orbital. And in the S we have how many? We have S in how many? 1, right? Write here 1. And in P how much? We have 3, so write here 3. And in the third cell you have again S, P, D, so 1, 3. And in the D, how many you have atomic orbital? 5, right? See here, 5. So write it here, 5. And in the fourth cell, you have 1 atomic orbital in the S, 3 in the P, 5 in the D, 7 in the F, right? Now write one more here, maximum number of electron. Maximum number of electrons. Now you tell me, you have here S, right? S cell, S subshell, right? So in the S subshell, how many you have atomic orbital? 1, right? So 1 into 2. How much will come? 2 electron. Right or not? Like that you have to do. So here 2 electron. And here 8 electron. How? 2 electron here, and here 3 into 2, 6. 6 plus 2, 8, right? Now here 1 plus 6 plus 10, how much? Here 2, right? Here 2. So 18 here. Here you can fill 18 electron maximum present in the third cell. Now in the fourth cell, you get here 32 electron. You can do it from yourself only, okay? You will get the idea how I am doing this, okay? Already I explained you, right? How to do this all, okay? So this is all about cell, subshell, atomic orbital, electrons, where the electrons are located, right? I hope I given the proper brief interview of atomic quantum mechanics and somewhat quantum mechanics, not in so much detail because this is the course of organic chemistry, okay? cell, subcell, atomic orbital, how to find the number of electrons in the subcell, how to find number of electrons in the cell, and all the things we discuss here. And I hope you learned something today, okay? And that is a basic part, okay? And that's a very important also, right? So if you found this lecture helpful, don't forget to like, share, and subscribe to Chemistry Portal for more chemistry insights, okay? And the links are given in the description box. You can join our Telegram channel. You can follow us on the Instagram, follow us on the Facebook, and subscribe to our YouTube channel. And see you in the next lecture. And we will discuss electronic configuration, Hoold's rule, Pauli principle, right? And all these things we will discuss in the next lecture. Thank you everyone. Thanks again.